Hello everyone, welcome to the lab 2 of ECE573 Advanced Embedded Logic Design. In this lab, we are going to discuss the reasons behind the poor performance of your hardware module. So in the lab 1, we have implemented the vector multiplication and we implemented this vector multiplication unit in the hardware. Now we need to understand why we are getting the poor performance in the hardware. So if you look at the function, we have written into the CPP file, and as we have discussed previously, this is converted into the RTL via HLS. So if you look at this HLS, so HLS report for this lab 1.1, if you open this HLS report, you will get the how this your CPP code is implemented in the hardware. So your clock frequency requirement is your FPGA clock frequencies period is 10 nanoseconds, and this is sufficient because you are able to complete your operation in 5.7 nanosecond. Okay, so that's what it is saying, that the target clock frequency is 10 nanoseconds, but you are able to complete your task in the 5.7 nanoseconds. The latency, like total number of clock cycle to implement your entire n element multiplication, is 225 clock cycles. And how 225 clock cycles, that we need to understand. To revisit what we are doing in our vector function, we are doing the element wise multiplications of between a and b, and n in our case is 32. So if we are doing the 32 multiplications, then to implement those 32 multiplications, this hardware is taking 225 clock cycle. Our expectation, that we were expecting that the one multiplication takes 1 clock cycle, so it should take maximum 32 clock cycle if they are implemented in serial, and if they are implemented in parallel, it should happen in 1 clock cycle. That was our expectation, but if you see in the HLS, it is taking 225 clock cycle, and we need to understand the reason behind it. So if you go into the loop here, you can see that this loop has a latency of 224 clock cycle. This loop is nothing but this for loop. Okay, so how to identify the loop, I'll discuss it sometime later, but right now assume that this loop is nothing but this for loop. And this for loop, if you go to the report, it is taking iteration latency. That means one iteration of this for loop takes 7 clock cycle. So what is the one iteration of this for loop? In one iteration, you are doing the one multiplications between the single element of A and single element of B and writing it into the output value. So it is taking 7 clock cycle. And then it is taking 7 clock cycle, and then you have 32 such iterations. So 32 into 7, you will get 224. So you can see trip count of that loop. Trip count means how many times that for loop will execute. It is 32 times because we have 32 elements, and it is 7. Each one iteration is 7, so that's why we are getting 224 clock cycles. And here it is saying that you have not pipelined the loop. That means we have not implemented it efficiently. How to pipelining the loop? What is the reason to pipeline the loop? We'll see it in soon. You can see that I'm using the DSP48, which is the embedded multipliers. I'm using the 3 multipliers. And here you just need to assume that in case of the floating point arithmetic, one multiplication takes 3 DSP48 units. Okay, 3 hardware multipliers. So for the floating point arithmetic, you need 3 multipliers. So that means your hardware is implemented using only single floating point multiplier instead of 32 multipliers. That was our assumption, but your hardware is implemented using a single multiplier, that is sequentially your operations are taking place. Okay, so we assume that we wanted to have the multiplication of all the 32 elements in parallel, but when we wrote the code and when the tool converted that code into the RTL code, it implemented in the sequential fashion. So this indicates that tool is not smart enough, and you need to instruct the tool to optimize the RTL code. And how to do that? For that, we need to understand how the HLS works. Okay, so what we need to do, whenever we write a C code and we are not getting the desired performance, we need to go to that hardware function, and then we need to click on this one where we will launch the HLS. So the HLS is nothing but the high level synthesis. Will open the HLS and will optimize your hardware code in the HLS. So I'll open the HLS. It will take 1 minute to open it, the HLS tool. Okay, so now the HLS is open. So you can see that this is the GUI of the HLS, and here you can see that in the source folder you will get your same vectmul.cpp file. So the code is not that complex, it is same, and this .h file you will see in the include one in your source one. You can see that the .h file is also included. Then you will see that here in the directive, your SDSoC tool has already added some directive in the HLS code. So these are the directives which are helpful to the HLS tool to optimize the code. Okay. In the separate lecture, we are going to study the meaning of all those directives. For now, we'll just assume that these are the some directives are being added by the tool. And if we want to optimize the code further, we can add those directives either in the SDSoC or here. So going to the results for this code, and we can see that we have already discussed these results, and you can see that here the loop takes 224 clock cycles, and your iteration latency is 7, so 7 into 32, 224, and it takes 1 clock cycle to enter inside the for loop, so that's why there is a additional 1 clock cycle. So I'll just add the name for this for loop, so for the better better referencing, so I'll just do the C simulation, run C synthesis, and you can see that then after this C synthesis, that means your functionality of the C code will be verified by this tool. Okay, so I have finished the C synthesis. Okay, and you can see that the results will be generated. And now if you see inside the loop, here you know that this is the loop which you have written. So it is always good to name up for each loop if you want to do the analysis in detail. Okay, so we have done, so we know this is taking so much time. Okay, and now you know how this came, you know how this came, but you don't know how this latency is 7. Why the one iteration is taking 7 clock cycle. Okay, so to understand this one, okay, what we need to go on the right hand top one, you need to go to the analysis perspective. So I click on the analysis perspective, and it will tell me why this loop one iteration takes the 7 clock cycle. So this is my loop. I'll just click on this one, and you will see that how these operations are happening. So you can see that initially I'm checking the I value. I am initializing the I value, then I'm doing the comparison of I value, and then I'm doing the increment of the I value. At the same time, I do the load of the new A and B. And since this A and B are stored inside the memory, that means I have to do the read operation, and it takes 1 clock cycle. So you can see that it takes 1 clock cycle. Then it do the multiplication. So here in the multiplication, you can see that it takes 3 clock cycle. So here, since we are doing the floating point arithmetic, it takes 3 clock cycle. That's why people say that the floating point arithmetic is expensive, and we should always use the fixed point arithmetic. It will reduce the significant complexity. But right now we are using the floating point arithmetic, so it is a significantly complex. So it takes 3 clock cycle, and then in the last clock cycle, you write the data back to your actual output. Okay, so that's why you are taking the total 7 clock cycle, and you have 32 iteration. You take the 224 clock cycle. Now you can see that here what is happening at each iteration. I am spending first 2 clock cycle on reading the value of A and B. Can't I do this operation when I am doing the multiplication in the previous iteration or if I doing the multiplication operation, now I can read the A and B value which I'll need in the next iteration. Can't I do this pipelining? So what is the pipelining? Pipelining means you shared your operations among the multiple clock cycles. Okay. For example, in this simple example, you can see that uh, at the beginning of each iteration, I'm spending 2 clock cycle on reading the A and B, but I can read those values in the previous iteration itself. Okay. And how to tell this to the tool is that you need to add the corresponding pragmas. Okay. So I'll go here, I'll go to the vector loop. Okay, vectmul, I'll go to this for loop, and what I'm going to do, I'm going to do the insert directive. Okay, then I'm going to select. So all these pragmas we are going to study it sometime later. So I'm going to do the pipeline. Okay, and here you need to make sure you add it to the source file, because we need to send this file back to the SDSoC. So it should be in the source file, and then I click on OK, and you can see that the corresponding pragmas is being added. Okay, so that means I'm telling the tool that pipeline this loop so that my execution time can be reduced. Now I'm doing the run synthesis, and after run synthesis, we'll see the our updated results. So I'm going to save the content, and let's wait for finishing this C synthesis. Okay, so my C synthesis is now finished, and if I go this, you can see now my clock cycles latency of that function execution has reduced from 224 to 39 just by adding one pragma. And now we need to go see why 39. Okay, so if you go to that loop, you will see that the loop latency is 7 clock cycle. Okay, but you have pipeline the loop, and that means, and here you can see the initiation interval. Okay, all these terms we'll discuss it in the when we'll discuss more about this HLS pragma. Initiation interval is the difference between the clock cycle when you can receive the new input. That means if I in this clock cycle I receive A of 0 and B of 0, after how many clock cycle I can receive A of 1 and B of 1. Initiation interval 1 indicate that I can receive the new input at every clock cycle. So that means I can input at every clock cycle. Okay, so ideally we want the initiation interval to 1, because we want to accept the new input at every clock cycle. Trip count will remain the same because it's a 32 iterations of the for loop, it will remain the same. And now we need to see if iteration latency is 7, obviously your operation it will take 7 clock cycle, then why it is 37. Okay, so that you need to understand. So here you can see that the iteration latency is 7, that is one iteration takes 7 clock cycle. And why? We have already discussed that you take 2 clock cycle to read the A and B, then you take 3 clock cycles to perform the addition, and then 1 clock cycle to perform the write operation. But since I am going to perform the read operation before I begin that actual iteration, I don't need to spend the 2 clock cycles on the read for every iteration. Okay, so that means the time required for the execution of the each loop will be each iteration will be significantly less. Okay, so here I'm going to accept the 32 inputs in the first 32 clock cycles. Okay, because I'm going to have the initiation interval of 1, that means I'm going to accept the 32 inputs for 32 clock cycle. Now first input, if I accept A of 0 and B of 0, that will be available at the corresponding 6 clock cycle, because last clock cycle takes for the write operation, so it takes around 6 clock cycle. So you can see that after I get the last input at the 32th clock cycle, I'm going to give the corresponding output at the 37th clock cycle. Okay, and then you can see that there is a additional delay of 1 clock cycle to write the data of the last output, so you get 38, and plus 1 clock cycle in the beginning to enter inside the loop, you get total 39 clock cycle. Okay, so this is how, by using the pipelining, we are able to get the improved performance. So once you add the corresponding pragmas, you have added the pragmas, you just need to close this HLS, and once you close this one, you will go back to the corresponding SDSoC tool, and you will see that the corresponding CPP file is already updated inside the SDSoC tool. Okay, so if you look at this CPP file, you can see that the corresponding pragma has been already added inside the CPP tool. Okay, so this is how you can add the HLS pragma inside the tool. So I have created the new project, which is a lab 1-2, which is around same as the multiplication. And what I have done, I have created the corresponding HLS, added the pipeline 1, and inside the main CPP, I have also done one modification. What I have done, I have, instead of using the malloc function, I have used the SDSalloc function. Okay, and what is this SDSalloc function? What it does, when you are assigning the memory addresses to the A in, B in, golden out, and actual out, it makes sure that these addresses are contiguous addresses. So all the 32 elements are stored one after the another. When you use the malloc function, it is not guaranteed that all these addresses are in the contiguous one. But when you use the this SDSalloc function, you are guaranteed that all these elements will be stored in the sequential fashion. So similar to the HLS pragmas, we have the other pragmas for the SDS. So, and we are also going to study all these pragmas and how to use it and when to use it. So right now I have just introduced you to the SDS one. So whenever you are using one variable for the hardware, make sure that you use the malloc and do not use the you use the SDSalloc and don't use the malloc function. Okay, because you need to understand that the hardware is going to read the data from the corresponding memory one. So it is always cheaper, or it is always more efficient to read from the contiguous location rather than using the different location. And why this is cheaper, we'll study it when we'll discuss the direct memory access one. Okay, so these are the two changes I have done. I have added the pragmas in my CPP code, and I have added the corresponding SDS free location, SDS free thing here. Now I have created the corresponding code, and what I can do, that I can run this code on the emulator, and I will see what we can get on the corresponding results. Okay, so I have completed the KEMU emulation, and you can see that I was able to get the slightly better execution time compared to the in the previous without the HLS. You can see that here I was getting 0.000012, and here I am getting 0.000022. So by using the small pragmas, I was able to get the slightly better execution time. Again, we can't trust the KEMU results. So what I'm going to do, I've created the project for the hardware, and I'm going to run the project on the hardware. So before that, I'll stop my emulator. Okay, so my SDX terminal is connected. So if you want to connect it, you just need to click on plus and then select the appropriate terminal. In case you have the access to the board. But if you don't have the access to the board, you can use the other method of Linux-based implementation. So in this case, the first the FPGA will get program, and after that, your ARM processor will get program. Okay, so the implementation has been completed, and you can see that on the we are getting the much better execution time or speed up on the hardware compared to the previous one where we have not used the HLS Pragma. Okay, so this is the one demonstration of how the HLS Pragmas can be used to improve the performance. Still, our performance is poor compared to the software, and this is because we are not able to do the n multiplications in parallel. And the issue is that when we are receiving the data from the PS, we are receiving it only one element at a time. And how to improve it further, or how to understand that which part of the algorithm or which section of the algorithm is suitable for the hardware, you not only need to take into account the how the hardware is being executed, but you also need to take account the how the data is being moved between the PS and PL. So in this video, we discuss about the how to add the HLS pragmas into the code which corresponds to the hardware section of your SDSoC.